Hello folks, this is Dr. Young, and in this video we're going to talk about the kinetic theory of gases and what it means for a gas to be kind of ideal and how do real gases deviate from that ideality. So first, right, just to kind of review, we talked about what gases were last time, kind of give an introduction, different things about, how much do their particles move compared to solids, or how dense are they compared to solids and liquids, things like that. But I did mention that, the universe is surrounded by gases, or the universe is made up of gases, mostly not surrounded by it. Well, I mean, our Earth is surrounded by it, but the universe is mostly made up of helium and hydrogen. The atmosphere we're breathing, right, is mostly nitrogen with some oxygen, argon, and some other trace gases like water and carbon dioxide. Speaking of carbon dioxide, greenhouse gases like carbon dioxide and methane are heating up the planet, causing climate change. Helium balloons obviously are filled with helium. When you bake things, use baking soda, or you let yeast do their things, like carbonated beverages like beers and stuff like that, sodas. Those are carbon dioxide. Same thing for your cakes and stuff like that have bubbles in them. That's carbon dioxide. Then there are toxic gases like carbon monoxide and lots of others, but carbon monoxide is a pretty common one that I think most people know. And then we also use gases as fuels. So natural gas is largely methane, has some other things in it, but largely methane, CH4. And then propane is a super common cooking gas. So C6H8 would be propane. So we see gases in lots of places. This is by no means an exhaustive list, but I just wanted to doubly emphasize how important these are and how much we see them. So the kinetic theory of gases. This is came from kind of like the 1800s or so. A lot of really great experiments were done to kind of come up with these. And what we're going to do in this video, in this lecture, is talk about each of these 5 different parts of it. And then at the end, we'll also talk about how real gases can deviate from these, either a lot or just a little bit, deviate from these 5 postulates here. And so what does the kinetic theory of gases mean, right? So kinetic refers to motion. So like kinetic energy, if you've had some physics before, is the energy of like objects in motion. And it's a theory because it helps us explain a lot about what we observe through the behavior of gases. And I'll just put this at the very bottom here, but the idea is that these are considered true for quote-unquote ideal gases. And ideal gases, the concept of an ideal gas is going to be explained by all 5 of these, like that they're volumeless and that they have random motion and they have no attraction. The gas particles have no attraction between each other. But what we're going to see throughout this chapter and this topic is that most gases behave fairly ideally in the conditions that we normally see them. So it's okay for us to model a lot of gas behavior using these 5 postulates. It seems to be okay. It's only at like really high temperatures or really low temperatures, really high pressures, and with certain gases that they deviate so much that we need to take that into account. So we will be talking a lot about like the ideal gas law and using it to model and make a lot of predictions about gases. And that's totally fine because, again, most gases in our typical range of temperatures and pressures that we experience behave ideally. So I'll just say these real quick, and then we'll go into each one in more detail. The first postulate is that gases are really tiny volumeless things that really don't change the volume of the container that they occupy, that they don't really take up space. So we consider them to be kind of volumeless. The second is that gases have constant and random motion. You might remember from that simulator I showed you in the previous video that these gases are just flying around willy-nilly. They don't really feel each other. They just bounce off at the angles that you would expect. That they're just random motion. They don't all move together or influence each other. The third is that gas particles have an average kinetic energy that's proportional to temperature. This is just saying that when you raise the temperature, you also speed up the movement of those particles, which again, I think we saw in that simulation that I showed you in the last video, that the temperature and the speed of the particle movement are related. The fourth says that when gases collide with each other, that the collisions are elastic, which means that they don't lose any energy when they bounce when they bounce into anything, really, whether it's the container that they're in or other gas molecules or whatever, that they bounce off without losing energy, that they're perfect elastic collisions. Now, really, elastic collisions are not a thing, but they basically behave that way. And then number 5, that there are no interactions between the gas particles. They neither repel each other nor attract each other. So let's look at each of these in a little bit more detail. First, that gases are tiny and volumeless, right? That's the first postulate of the kinetic theory of gases. And we're saying that an ideal gas behaves as though it is volumeless. And that means that it's not going to change the volume of the container that it's in. That basically, and let me go ahead and write that. What we're saying here is that the volume of the container is about the same with or without the gas in it. And really, I should say the volume of empty space in the container. Let me say that, the volume of empty space in the container. That putting gases in it really doesn't change anything. So write this, the volume of empty space in the container is about the same with or without the gas in it. So if I have this container here, right, the idea is that I can add a couple of like gas particles, but they're so small. I don't even know if you can see this. You might think it's just dust on your screen, but they're so small that really they're not changing the volume of the container. And so we can do all these calculations based on that assumption that the volume of the gas really is negligible. We can ignore it. And that would be true for ideal gases. It's not true in reality, but it is true for real gases, for ideal gases. The second is that gases have constant and random motion. And again, when you watch that video, you probably saw the gas molecules, right? They're just totally bouncing around in random motion. They're not really influencing each other's motion. They're not all going in the same place, right? So it's not like all the gas molecules are like, okay, everybody, let's go to the right first, and then we'll go left, and then we'll move upwards, right? They don't all do this, right? This is not a thing. No. They don't have a random, they don't have like a coordinated movement, right? They're not feeling each other, they're not oscillating together or anything like that. What we saw was that, you know, that one might be going this way, and this is going that way, and that one's going there, and this one's there, and that one, I mean, they just were just kind of flying around in like any direction whatsoever. You know, they're just kind of all doing their own little thing. So they do have really random and constant motion, and that is a really good description of all gases, ideal or real. They don't tend to really influence each other's movement very much at all. So that's a really good postulate of the kinetic theory of gases. Now the third, sorry, this says 4. The third, if I can count, the third is that gas particles have an average kinetic energy that's proportional to the temperature. And right, so if you look at kinetic energy, which is Ke, right, and again, this is the energy of moving things, of moving objects. The idea is that kinetic energy is equals 1/2 of the mass of the object that's moving times the velocity squared. The velocity squared. Velocity is just speed with a direction, if you haven't had any physics before, but it's kind of equivalent for us to speed. It's just speed in a direction, but it's basically speed. So what this is saying here, right, is that the kinetic energy, which basically is an approximation for temperature, right, that this temperature is proportional to, that's what this little alpha means, it's proportional to the speed, or in other words, the velocity. So if you increase the temperature, you increase the average speed of the particles. If you decrease the temperature, you decrease the speed of those particles. And again, I showed you that in that simulation, right? I increased the movement of them by increasing the temperature. I was able to get them to fly around faster that way. What this graph over here on the left is showing here, right? First, we're starting off with 300 degrees, at 300 degrees Kelvin, Kelvin, which is about 30 or so degrees Celsius. Those gas particles, you may remember from the simulation, right? They didn't all move the same speed. Some move faster, right? So here's a faster speed, but there's not many particles, right? The y-axis is the fraction of particles, like what percent of the particles. And then the x is the speed here, right? So not many, but some were moving really quick. And not many, but some were moving really slow, right? Most of them, right? A lot of them were moving this sort of average speed here. And so there we have this dotted line to show the average. But they're not all moving at a given temperature. Not all the particles of gas are moving at the exact same speed. There's some variance. Some are a little faster, some a little slower, but you can get an average. Now, what we're saying, right, is if we increase the temperatures to say 1,000 Kelvin, then your average has moved up, right? Now your average is here. Before your average was down here. And so you're able to increase the average speed, the average velocity of all of these little particles. And then you could go on even further, right? You've got the 200 Kelvin, and then, 2000 Kelvin, and then it moves even faster. So that is totally fair. Absolutely. If you increase the temperature, you're going to increase the speed of the particles. That is definitely true for ideal and non-ideal gases. Now 3 and 4 here. So 3 says that when the gas particles collide with one another or anything, that the collisions are considered elastic, which means they do not lose energy, right? So that's the big thing, is that they do not lose energy after a collision. Right? They don't generate any heat. That's usually how things kind of get rid of some energies. They generate a little bit of heat, and that energy goes away, right? We all have played with a bouncy ball of some sort, basketball, any kind of ball. When you drop it, right, it bounces back up, but maybe not quite as high, and then it bounces again, and maybe not quite as high, and then not quite. Right? So it loses energy. It's not a perfectly elastic collision. If your bouncy ball was elastic, like we're saying these gas particles are, then when you bounced it and it hit the ground, it would bounce right back up to the exact same spot, and then it'd bounce and it'd come right back up to the same spot over and over and over again, forever and ever. That is not true for real gases, but it is true enough for ideal gases. Right? So what we're saying is that if this gas particle here bounces off of the side of the wall, just ricochets off, the energy that it had before, so I'll say its initial energy, equals the energy that it has afterwards, its final energy. So it didn't lose any energy, it didn't generate any heat when it bounced. Same thing for if two particles hit one another. They'd have the same energy is the idea. Now the last one's the hardest for me to explain to you all right now because you don't know what attractive forces are. But this is saying that there's no interactions between gas particles. So we're saying no attraction. There's no attraction between particles or repulsion. Right? It's not like two particles are going to like repel one another, that these are going to repel each other somehow, so they're going to try to get away. And it's also not true that two particles would be attracted to one another, right? That they're going to feel each other's attraction and want to glom together. What we're saying is that for ideal gases, there are no attractions. Now, real gases do feel some attractions, especially if they have certain types of attractive forces, like hydrogen bonding or something like that. But this is going to be true enough for most gases that we can say, generally speaking, for ideal gases, quote unquote ideal gases, that there are no attractions between particles, that there's no attraction, no attractive forces, I'll say. So no attractive forces. No attractive forces between the particles. And I'll talk a little bit more about that in a second. So those are the big five. Those are the big five postulates of the kinetic theory of gases. So here they are one more time for you, right? Just the gases are tiny. So this is for ideal, right? So this is for ideal gases. What we're saying is that ideal gases are volumeless. Ideal gases have constant random motion. For ideal gases, temperature and speed are proportional to one another. We're saying that for ideal gases, for ideal gases, they have elastic collisions. They do not lose energy when they bounce into things. And we're saying that for ideal gases, there are no interactions between the gas particles. They don't feel each other at all, neither repulsion nor attraction. Now, real gases, sometimes called non-ideal gases, real gases can deviate from the ideal gas law. And we'll talk about the ideal gas law itself more in a second. But again, for most all of the time, we can consider all of the gases that we encounter as being pretty ideal. But that being said, real gases deviate when the gases have a really large volume, right? So if you compare something like helium, which is very, very small, it's going to behave ideally. It behaves pretty ideally. But if you go into a much larger atom like krypton is very big, it behaves non-ideally. Because it's just so big that it's going to have some different properties, right? So it behaves non-ideally. Right? And that's because if it's big, it has a volume, right? It's not going to be volumeless. It doesn't act like it's volumeless because it takes up so much space. It's so large that it's now going to deviate, and those calculations that we're going to be doing are not going to be as valid. We're going to have to make modifications to those. The other thing that real gases deviate, or when real gases deviate a lot from the gas law, is when they do have strong attractive forces. So things like hydrogen bonding or large dipoles or something like that. At this point, we don't really know much about attractive forces, so we have to kind of ignore that. But some things, again, like helium, they don't really have attractive forces, so they do behave ideally. But things like water have quite strong attractive forces. So water will behave less ideally because it has those attractive forces, and water molecules do want to glom together. They do want to stick to one another, whereas helium atoms do not. So we'll talk more about attractive forces later, but I just kind of want to put this on your radar now. At high pressures, the gases are closer together and are less volumeless, right? So if you have really high pressure, the idea is that there's going to be a lot of particles in a little space, so the amount of space that they take up in that container is not negligible anymore, that they do actually take up a significant amount of volume, and that's going to change your calculations. And then the last one, at low temperatures, attractive forces, again, start to take over. At low forces, you're going to start to get things to condense and start to try to turn back into liquid phase, or these gas molecules are going to try to stick to each other more. And so again, you deviate from your ideal gas law. I'm not really concerned that you all can calculate this. There are certainly ways that you can calculate this. There's even some in the book. Don't really care. I just want you to know generally why a real gas would deviate from the ideal gas law. So going forward, though, we are going to treat most gases as being ideal. So in our next video, we're going to talk about the ideal gas law, PV equals nRT, and how to use it to solve questions, to solve problems and answer questions about the pressure, the volume, the temperature of the gas that we might be wondering about. So keep an eye out for that video. Happy studying. Good luck.